Hi there, future teacher. Welcome to your MTTC 093 Integrated Science Study Guide, covering Subarea 4, Physical Science, proudly presented by TeacherPreps.com. Physical science makes up 25% of the exam, with 8 objectives spanning chemistry, physics, mechanics, energy, and waves. By the end of this lesson, you will have the knowledge you need to confidently tackle every physical science question on test day. Let's get started. Before we dive in, here is something to help you get the most out of this lesson. Research shows that students who actively take notes retain up to 29% more information than those who passively watch. So we created a completely free study guide workbook that follows this exact video. It includes all the key terms, comparison tables, practice questions, and plenty of space for your own notes. To get your free copy, just click the link in the description below. This lesson is presented by TeacherPreps.com, your partner for teacher certification exam prep. Our complete program includes in-depth study guides for every content area, full-length timed practice tests that mirror the real exam format, interactive vocabulary exercises, and constructed response practice with AI scoring. It is free to get started. Alright, that was our plug. For the rest of this video, it is go time. Grab your pen and paper, and let's learn some physical science. Here is what we are covering today. Subarea 4, Physical Science, has 8 objectives. We will start with the chemistry of matter, atomic structure, the periodic table, elements versus compounds versus mixtures, and chemical symbols and formulas. Then we move to chemical changes, reactions, bonds, balancing equations, and reaction rates. After that, we cover the physical properties of matter, density, states of matter, and phase changes. Next up is the kinetic molecular model and gas laws. Then we shift to mechanics, Newton's laws, force, work, power, and simple machines, followed by electricity, magnets, and electromagnetism, then energy and thermodynamics. And we finish with waves, sound, light, and optics. Let's begin with Objective 16, the chemical properties of matter. Let's start with atomic structure. Every atom has 3 subatomic particles. Protons carry a positive charge and sit in the nucleus. The number of protons defines which element it is. That number is called the atomic number. Hydrogen has 1 proton, carbon has 6, oxygen has 8, iron has 26. Neutrons are also in the nucleus, but carry no charge. They contribute to the atom's mass, but do not affect its chemical identity. And electrons carry a negative charge and orbit the nucleus in energy levels, also called shells. The first shell holds up to 2 electrons, the second holds up to 8, and the third also holds up to 8. The electrons in the outermost shell are called valence electrons, and they determine how an atom behaves chemically. Atoms want a full outer shell. This desire for a complete set of valence electrons is called the octet rule, and it is the driving force behind chemical bonding. The standard model taught at the elementary level is the Bohr model, which shows electrons orbiting the nucleus in distinct circular shells. Now let's connect atomic structure to the periodic table. The periodic table is organized by atomic number, increasing from left to right and top to bottom. Rows are called periods. The period number tells you how many electron shells that element has. So elements in period 1 have 1 shell, period 2 has 2 shells, and so forth. Columns are called groups or families. Elements in the same group have the same number of valence electrons, which is why they share similar chemical properties. Group 1 elements are the alkali metals, like sodium and potassium. They have 1 valence electron and are highly reactive. Group 2 is the alkaline earth metals, like calcium and magnesium. They have 2 valence electrons. Group 17 is the halogens, like chlorine and fluorine. They have 7 valence electrons and are very reactive nonmetals. And Group 18 is the noble gases, like helium and neon. They have a full outer shell, so they are stable and almost completely unreactive. On the left side of the table, you find metals. Metals tend to lose electrons, conduct electricity, are malleable, and are shiny. On the right side are nonmetals. Nonmetals tend to gain electrons and are poor conductors. In between are the metalloids, like silicon and boron, which have properties of both metals and nonmetals. Now, a critical classification you need to know: elements, compounds, and mixtures. An element is a pure substance made of only one type of atom, gold, oxygen gas, and carbon are all elements. A compound is a pure substance made of two or more elements chemically bonded in a fixed ratio. Water, H2O, is always two hydrogen atoms bonded to one oxygen atom. Table salt, sodium chloride, is always sodium bonded to chlorine. Carbon dioxide, CO2, is always one carbon and two oxygen. A mixture is two or more substances physically combined but not chemically bonded. There are two types of mixtures. Homogeneous mixtures, also called solutions, have a uniform composition throughout. Salt water, air, and brass are homogeneous mixtures. Heterogeneous mixtures are not uniform. Trail mix, salad, and oil and vinegar are heterogeneous. Here is the key difference for your exam. Compounds can only be separated by chemical reactions. You cannot physically pull hydrogen and oxygen out of water. You need electrolysis. But mixtures can be separated by physical methods like filtration, evaporation, magnetism, and distillation. Let's talk about reading chemical symbols, formulas, and expressions. Every element has a 1 or 2-letter symbol. H is hydrogen, He is helium, Na is sodium, Fe is iron. Chemical formulas tell you which elements are present and how many atoms of each. In H2O, the subscript 2 means there are 2 hydrogen atoms, and the O with no subscript means 1 oxygen atom. In CO2, there is 1 carbon atom and 2 oxygen atoms. Glucose, C6H12O6, has 6 carbons, 12 hydrogens, and 6 oxygens. When you see a coefficient in front of a formula, like 2H2O, that means 2 molecules of water. That gives you 4 hydrogen atoms total and 2 oxygen atoms total. In a chemical equation, the arrow means yields or produces, and the plus sign separates multiple reactants or products. For example, 2H2 plus O2 yields 2H2O reads as 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water. Let's check your understanding with a practice question. A teacher shows students a substance that is composed of 2 types of atoms bonded together in a fixed ratio and cannot be separated by physical means. Which classification best describes this substance? Is it A, an element, B, a homogeneous mixture, C, a compound, or D, a heterogeneous mixture? Pause the video and think about it. We will reveal the answer at the end of the video. Moving on to Objective 17, Chemical Changes. A chemical change produces new substances with different properties from the original. How do you know a chemical change has occurred? Look for these signs: a color change, gas production or bubbling, a precipitate forming, which is a solid forming in a liquid, energy being released or absorbed, which you might notice as a temperature change or a new odor. Contrast this with physical changes, like melting ice, dissolving sugar, or cutting paper. Those change the form or appearance, but do not create new substances. Let's talk about acid-base reactions. Acids produce hydrogen ions, H+, in solution. They taste sour and turn blue litmus paper red. Common acids include vinegar, which is acetic acid, citrus juice with citric acid, and stomach acid, which is hydrochloric acid. Bases produce hydroxide ions, OH-, in solution. They taste bitter, feel slippery, and turn red litmus paper blue. Common bases include baking soda, soap, and ammonia. The pH scale runs from 0 to 14. A pH below 7 is acidic, pH 7 is neutral like pure water, and above 7 is basic. When an acid and a base react, they neutralize each other. Acid plus base yields a salt plus water. For example, hydrochloric acid plus sodium hydroxide yields sodium chloride, which is table salt, plus water. Now let's cover oxidation-reduction reactions, also called redox reactions. These involve the transfer of electrons. The substance that loses electrons is oxidized. The substance that gains electrons is reduced. A helpful mnemonic is oil rig. Oxidation is loss, reduction is gain. Everyday examples of redox reactions include rusting, where iron reacts with oxygen to form iron oxide. Combustion, or burning, is another redox reaction. When wood burns, it is being oxidized rapidly. Tarnishing silver and batteries generating electricity are also redox processes. In batteries, a chemical redox reaction drives electrons through an external circuit, producing electrical current. Now let's talk about chemical bonds. An ionic bond forms when one atom transfers electrons to another. This typically happens between a metal and a nonmetal. Sodium has one valence electron it wants to lose. Chlorine has 7 and wants one more. Sodium transfers its electron to chlorine, forming sodium plus and chlorine minus ions. These oppositely charged ions attract each other, creating sodium chloride. Ionic compounds have high melting points, dissolve in water, and conduct electricity when dissolved. A covalent bond forms when atoms share electrons. This typically happens between two nonmetals. In water, oxygen shares electrons with two hydrogen atoms. In oxygen gas, O2, two oxygen atoms share two pairs of electrons in a double bond. Covalent compounds tend to have lower melting points, may not dissolve in water, and do not conduct electricity. Metallic bonds, where electrons are shared among many metal atoms, explain why metals conduct electricity and are malleable. Balancing chemical equations is a must-know skill. The law of conservation of mass says matter cannot be created or destroyed in a chemical reaction. That means you must have the same number of each type of atom on both sides of the equation. Let's walk through an example. The unbalanced equation is iron plus oxygen gas yields iron 3 oxide. Written as Fe plus O2 yields Fe2O3. Count atoms on each side. Left side, 1 iron, 2 oxygen. Right side, 2 iron, 3 oxygen. Not balanced. Step 1. Balance iron by putting a 4 in front of Fe on the left and a 2 in front of Fe2O3 on the right. Now we have 4 iron on each side. Step 2. The right side now has 6 oxygen atoms, so put a 3 in front of O2 on the left. Now left side, 6 oxygen. Right side, 6 oxygen. Final balanced equation. 4 Fe plus 3 O2 yields 2 Fe2O3. The key rule is only change coefficients, the numbers in front of formulas. Never change subscripts, because that changes the substance itself. What factors affect how fast a chemical reaction happens? There are 5 main ones. First, temperature. Higher temperature means particles move faster and collide more often and with more energy. Food spoils faster at room temperature than in a refrigerator. Second, concentration. More reactant particles in a given space means more frequent collisions. A fire burns more intensely in pure oxygen than in air, which is only 21% oxygen. Third, surface area. Smaller pieces expose more surface for reactions. Powdered sugar dissolves almost instantly compared to a sugar cube. Fourth, a catalyst speeds up a reaction without being consumed itself. Enzymes in your body are biological catalysts that speed up digestion and other biochemical reactions. Fifth, the nature of the reactants themselves matters. Some substances are inherently more reactive than others. Now, chemical equilibrium occurs when the forward and reverse reactions happen at equal rates. Le Chatelier's principle states that if you disturb an equilibrium, the system shifts to counteract the change. For example, when you open a bottle of soda, the CO2 gas escapes, so the equilibrium shifts to produce more gas, which is the fizzing you see. Objective 18 covers physical properties of matter. Let's start with density, mass, and volume. Mass is the amount of matter in an object, measured in grams or kilograms. Volume is the amount of space an object takes up. Density is mass divided by volume. D equals m over v. Density determines whether something floats or sinks. Water has a density of 1 gram per cubic centimeter. Objects less dense than water float. Objects denser than water sink. Let's work an example. A block has a mass of 200 grams and a volume of 50 cubic centimeters. Its density is 200 divided by 50, which equals 4 grams per cubic centimeter. Since 4 is greater than 1, this block sinks in water. What floats because its density is about 0.5 grams per cubic centimeter. And even though ships are made of steel, which is very dense, the overall density of the ship, including all the air inside, is less than water, so it floats. Here is a distinction your exam loves to test. Weight versus mass. Mass is the amount of matter in an object. It stays the same everywhere, whether you are on Earth, the Moon, or floating in space. Weight is the force of gravity on that mass. Weight equals mass times gravitational acceleration, W equals mg. On Earth, G is approximately 9.8 meters per second squared. On the Moon, G is about 1.6 meters per second squared, roughly 1/6 of Earth's gravity. So a person with a mass of 60 kilograms weighs about 588 newtons on Earth, but only about 96 newtons on the Moon. Same person, same mass, much less weight. Mass is measured with a balance by comparing to known masses. Weight is measured with a spring scale, which measures gravitational pull. Now let's cover the states of matter. There are 3 common states. In a solid, particles are tightly packed in fixed positions and vibrate in place. Solids have a definite shape and a definite volume. In a liquid, particles are close together but can slide past each other. Liquids have a definite volume but take the shape of their container. In a gas, particles are far apart and move rapidly in all directions. Gases have no definite shape and no definite volume. They expand to fill any container. There is also a 4th state called plasma, which is a superheated gas where electrons are stripped from atoms, creating ions. Plasma is found in stars, lightning bolts, and fluorescent light bulbs. Phase changes are transitions between states of matter. Melting is solid to liquid. Particles gain enough energy to break free from their fixed positions. Freezing is the reverse, liquid to solid. Evaporation and boiling convert liquid to gas. Particles gain enough energy to escape. Condensation is the reverse, gas to liquid. Sublimation is when a solid goes directly to a gas without passing through the liquid phase. Dry ice, which is solid carbon dioxide, is the classic example. And deposition is gas directly to solid, like frost forming on a cold window. Here is a critical concept. During a phase change, the temperature stays constant even though you are adding or removing energy. That energy goes into breaking or forming the bonds between particles, not into increasing temperature. This is called latent heat. Endothermic phase changes absorb energy, melting, evaporation, and sublimation. Exothermic phase changes release energy, freezing, condensation, and deposition. Let's connect physical properties to practical uses. Metals like copper have high electrical conductivity, which makes copper ideal for wiring. Glass is transparent, so it is used for windows. Rubber is flexible and durable, perfect for tires. Steel is strong, so it is used in building construction. Thermal conductors like metals are used for cooking pots because they transfer heat efficiently. Thermal insulators like wood, plastic, and fiberglass are used for handles and home insulation because they resist heat transfer. Water has remarkable properties. It has a high specific heat, which means it absorbs a lot of heat without much temperature change. This moderates coastal climates. Water expands when it freezes, which is unusual. Ice is less dense than liquid water, so it floats, insulating lakes from the top and allowing aquatic life to survive winter. Water is a polar molecule, making it an excellent solvent. It also has high surface tension and exhibits capillary action, which helps water travel up plant stems. For separating mixtures, remember these methods. Filtration separates solids from liquids. Evaporation recovers dissolved solutes. Distillation separates liquids with different boiling points. And magnetism separates magnetic materials. A classic exam question. To separate a mixture of sand, salt, and iron filings, first use a magnet for the iron, then add water to dissolve the salt, filter out the sand, and evaporate to recover the salt. Objective 19 covers the kinetic molecular model and gas laws. The kinetic molecular theory has 5 key assumptions. First, matter is made of tiny particles in constant motion. Second, the kinetic energy of particles is proportional to temperature. Third, gas particles are far apart with negligible volume compared to the container. Fourth, particles move in straight lines until they collide. And fifth, collisions are perfectly elastic, meaning no kinetic energy is lost. This model explains gas pressure. Particles hitting the container walls create outward force. It explains temperature as the average kinetic energy of particles. And it explains diffusion, which is particles spreading from areas of high concentration to low concentration. That is why you can smell perfume from across a room. It also explains why gases are compressible but liquids and solids are not. Gas particles have lots of empty space between them. Now for the gas laws. Boyle's law says that at constant temperature, pressure and volume are inversely proportional. P1 times V1 equals P2 times V2. If you squeeze a balloon, reducing its volume, the pressure inside increases. A scuba diver descending feels the air in their lungs compress as water pressure increases. If a balloon has a volume of 3 liters at 1 atmosphere, and the pressure increases to 3 atmospheres, the new volume is 1 times 3 divided by 3, which equals 1 liter. Charles's law says that at constant pressure, volume and temperature are directly proportional. Heat a gas and it expands. This is how hot air balloons work. Heating the air inside the balloon increases its volume, making it less dense than the surrounding air, so it rises. Gay-Lussac's law says that at constant volume, pressure and temperature are directly proportional. A sealed aerosol can in a fire has rising temperature, which causes rising pressure, which can cause the can to explode. The combined gas law puts them all together. P1V1 over T1 equals P2V2 over T2. Remember, always use absolute temperature in Kelvin. Kelvin equals Celsius plus 273. And Avogadro's law states that equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. Practice question number 2. A sealed balloon is placed in a freezer. What happens to the balloon and why? Is it A, the balloon expands because gas particles gain energy in the cold? B, the balloon shrinks because decreasing temperature reduces the volume of the gas inside? C, the balloon stays the same size because the number of gas molecules has not changed? Or D, the balloon pops because the gas particles freeze and expand? Think about which gas law applies here. Pause the video. Great work so far. You have covered the chemistry and gas law objectives. That is objectives 16 through 19. But here is the thing. Those 4 objectives are only half of physical science. You still need to master objective 20, mechanics, objective 21, electricity and magnetism, objective 22, energy and thermodynamics, and objective 23, waves and optics. Without those, you are walking into test day with only half the preparation you need. The complete study guide covering all 8 objectives, plus full-length timed practice tests, is available right now at TeacherPreps.com. Link in the description.